Hello everybody, welcome back to Glaciers and Glacial Geomorphology. In this session I just want to say a few brief words about glacier surging and fast flow. Now these are topics that we could spend an entire degree program on and then a couple of PhDs, but I just want to go through them very briefly on this occasion to tie up some loose ends regarding what we've been saying over the last few sessions about glacier movement before we move on to our next few topics. If this is an area that you'd like to explore in more detail, then it's obviously a topic that you could choose for your coursework essay, and that will give you an opportunity to explore it in a lot more detail. But all I want to do today is make a few brief comments just to flag up this topic as being something which is relevant to the course, even though it's not something that we're going to focus on this occasion. We typically talk about glaciers having one of three different flow regimes. Most glaciers come under the category of normal flow, which is what we think of as being centimeters to meters per year, typical glacier speeds. But a few glaciers, for example ice streams, flow much faster than that. And some glaciers switch between periods of fast flow and periods of slow flow. And you might remember right back at the beginning of this module we talked about Cam's classic 1987 paper where he was trying to explain some of the reasons behind why some glaciers might surge. So you've been familiar with this for a while. Now this really helpful diagram from Clark's 1987 paper illustrates those different flow regimes. So what the graph is showing is the year, the date 1600, 1650 through to the year 2000 on the bottom axis, and up the side axis the velocity in meters per year of different glaciers. Notice it's a logarithmic scale, so we're going 3, 4, 5, 6, 10 meters, 20, 30, 40, 100 meters, 1,000 meters, 10,000 meters per year. And you'll see, for example, White Glacier here has a velocity of about 10, 20, 30, 40 meters per year steadily over a long time period. Other glaciers, for example, looking here at Ice Stream B in Antarctica, much higher flow rates. Others, such as Jakobshavn, even higher. And it is possible for these flow rates to change over time. Look at another of the Antarctic ice streams, Ice Stream C, which appears to have switched off at some point and transitioned from this fast flow regime into virtually a stagnant regime, but a very slow flowing regime since about that time. And finally, look at the variegated glacier here, which fluctuates extremely between having flow velocities of the order of tens of meters per year to very short periods where the flow velocities exceed even the fastest rates of glaciers such as Jakobshavn glacier, and then returns to normal. And then after a quiescent phase, another surge. Quiescent and another surge, and this rapidly fluctuating regime, that's what surging glaciers look like on this kind of graph. We mentioned ice streams there as an example of one of the fast flowing glacier types. Just make sure you're familiar with the concept of an ice stream. We talked about it earlier in the module when we were talking about different types of glaciers in the first couple of sessions. This map illustrates the flow velocities around the Antarctic ice sheet, and you can see from the scale on the left very slow flowing ice is marked in blue and then up through yellow towards red for faster and faster flowing ice. And you can see the ice shelves are moving very quickly, but also some of these literally streams of ice feeding into the ice shelves, and at other locations particularly around the edge of Antarctica, these ice streams are flowing at extremely high speeds. This next image zooms in. You can see here's Antarctica, and here's where we've zoomed into looking at the ice streams flowing into the Ross ice shelf. These used to be named just by letters ice stream A, B, C, D, E, etc. But more recently they've been given names associated with well-known glaciologists. But this diagram again shows, this map again shows in some detail the velocity variations between ice within these fast-flowing zones and ice outside the fast-flowing zones. And you can see here Ice Stream C that we mentioned previously, which at the moment isn't a fast flowing stream. It's a former ice stream. You can see where its position was, but at present it doesn't experience those fast flow velocities in the same way that the ice streams on either side of it are doing. Now in this session I'm actually not going to spend a lot of time explaining why ice streams have these fast flow velocities, partly because it's very easy for you to get into the literature and have a quick look at that, but mainly because I'm confident, and what I'm really concerned about at the moment is that you should be able to come up with ideas about why these zones might be fast flowing in terms of what's going to accommodate fast flow within portions of an ice stream, within portions of an ice sheet. And I'm sure that based on what we've been doing in the last few sessions, and this is kind of why we're looking at this topic now, it's partly a test to see how you get on with this. On the basis of what we've done in the last few sessions, I'm confident, and I hope, that you will be able to think about mechanisms such as subglacial deformation. Could that be responsible? And if so, how would that work? Could it be enhanced sliding in some location for some reason, and what would the reason be? Could it be to do with enhanced creep, and how would that relate to ice temperature? So what I'd like you to do, before looking up the right answers to why the ice streams are moving in the way that they are, just think through, as a form of revision for what we've done previously, what you think could be the explanations for faster flowing ice. Would you need a more or less deformable bed? Would you need higher or lower basal water pressure? Would you expect warmer or colder ice temperatures, depending on the particular mechanism that might be underpinning this faster flow? Also have a think about Jakobshavn Glacier in Greenland, which is a glacier with a floating terminus, and have a little think about how that could affect the properties of the flow properties of that ice stream coming off the Greenland ice sheet. Then go and have a look at the literature and read up on the research that's been done on these ice streams in recent work. The other topic I want you to think about is glacier surging, or the topic I want you at least to be aware of at this stage is glacier surging. And a glacier surge involves periodic rapid movement of ice within a glacier, alternating with longer periods of stagnation. Now bear in mind there, it isn't necessarily that the whole of the glacier moves all at once. What we're talking about typically is a kinematic wave moving through the glacier. In other words, a portion of the glacier which is moving faster than the ice around it, but the position of that fast moving portion itself migrates down glacier over the course of the surge. And this diagram from Patterson illustrates what impact that can have on the morphology and the extent of a glacier. This is a glacier with its profile marked for different dates. So 1962, thicker, steeper and shorter profile. 1964, a surge, ice is transferred from the upper portion to the lower portion, so we have a thinner, more gently sloping and more extended glacier. Then during the quiescent phase we have down wasting of this dead ice at the front of the glacier, and gradually a build-up of ice in the accumulation zone, building back to towards that initial phase. What it looked like in 1962, it would also look like after some period of time after the surge. It regains that initial shape, and typically with surging glaciers, after it regains its initial profile, it's likely to undergo another surge. Bear in mind, we'll come back to this later in the course, but bear in mind also that surging has a geomorphic impact, and I've put some reading for that onto the KLE for this session. Now, a couple of things for you to think about in terms of surging. First of all, as we talked about with ice streams, it's a question of what is the fast flow mechanism. Is it because of enhanced deformation or faster sliding? And is that because of a change in water pressure, or is it what's going on in terms of allowing the glacier to flow so fast? And secondly, what's the on-off switch? What triggers a surge, and why is it that surges occur in this intermittent fashion with a surge phase, typically relatively short, followed by a typically much longer quiescent phase? What is it that's switching the surge on and off? A couple of NBs there. First of all, as I just mentioned previously, make sure you're comfortable with the idea of a kinematic wave, and secondly, make sure you have some examples of different types of glaciers that have experienced surging. And initially we'll talk about some of the classic theories as to why glaciers surge, and the classic examples there are variegated glacier in Alaska as an example of glacier surging on a rigid bedded glacier, and Trapridge Glacier in the Yukon as an example of soft bed surging. when you've familiarized yourselves with the classic theory and those well-known examples, there's a lot of very recent work ongoing on glaciers, particularly work by Doug Benn and his colleagues, that it's important for you to be aware of, and I'll bring you back to that at the end of this session. One of the most famous bits of research on surging glaciers is research that's been carried out at the Variegated Glacier, in particular research that was associated with a surge in 1982 to 1983, where the surge had been predicted, because surges typically happen on a regular periodicity, so the surge had been predicted, and so everything had been set up to monitor this surge. And what was recognised, so you can read up on this in the literature in more detail, but what was recognised was, as we specified previously for being characteristic of a surge, this zone of fast-flowing ice within the glacier that initiated in the upper portions of the glacier, and then that zone of fast-moving ice, so it isn't that the whole glacier suddenly starts moving forwards, but there's a zone within the glacier within which the ice is moving quickly. The position of that zone then migrates down glacier. The rate of migration of the zone of fast-moving ice doesn't necessarily match the actual speed of movement within that ice. That's what a kinematic wave is like. Think of it as a gap in a traffic jam, for example. The gap can move backwards or forwards up the traffic jam, not necessarily at the speed that the cars themselves are moving, and not necessarily at the speed that the front or back of the jam itself is moving. So it's motion within the glacier. So below this surge front, below the fast-moving zone, velocities were very slow, and within that fast-moving zone, velocities were very high, higher than greater than 20 meters a day. So that means that above the surge front, we're essentially extending or stretching out the ice, and below the surge front, we're effectively compressing the ice as the surge front migrates through the glacier. Now, the observations revealed some clues that, again, I'm hoping you will be able now to think through and think, well, what does this mean about what might be causing the surge? So during the surge, the basal water pressure was very high. So they had boreholes drilled down through the ice to the bed, and the level of the water in the boreholes was very deep. Bits of water that were escaping from the glacier were very clean, low turbidity, not much debris in them. But then at the end of the surge, lots of water came out, the water pressure within the glacier dropped, and the water that was coming out was very dirty, high turbidity. So what does that mean? Well, one hypothesis that you might have come up with as I was just talking through that is that, well, if the water pressure is high, there's not much water coming out and it's very clean water, then during the surge or prior to the surge, water is being stored at the bed and not escaping. So the dirty water from the bed is being kept within the glacier. That's leading to high basal water pressures, which are going to reduce the friction and enable sliding to occur. And then at the end of the surge, that water is released, so the water pressure it drops. The water that's coming out is dirty because it's been in contact with the bed, and that drop in water pressure leads to the friction at the base re-establishes itself, and the fast movement stops. And so the hypothesis that emerges from that is that there's a periodic evolution of the drainage network, whereby at some periods meltwater can escape very easily, perhaps through a tunnel or channelized system, and at other times the overburden pressure of ice perhaps crushes down that channel system and reduces the subglacial hydrology to a linked cavity system. And that should sound familiar to you, because that's what Cam was talking about in that 1987 paper, these linked cavities. And in a linked cavity system where the water can't escape very quickly, then we're going to be talking about increases in basal water pressure and reductions in friction, whether you have a very efficient channelized or tunnel-based outflow system. The water can escape quickly, and we're not going to be building up that high basal water pressure. And that kind of underpins one of the traditional theories of how surges happen, which is to do with cyclic variability in the seasonal closing up of the subglacial drainage network. So when the glacier is at a certain thickness, when the head of the glacier reaches a certain critical thickness, that overburden pressure is sufficient to close down the drainage system over the winter, so that when the spring meltwater comes along, it has nowhere to go, and the high basal water pressure within this linked cavity system enables surging to occur, and then when the water is released, the tunnels open up, surging doesn't occur, and when the glacier isn't so thick in that upper sections, then the system doesn't close down at all over a winter, and so we don't have the surges occurring until the glacier regains that previous state. Now you could apply this equally, you could think this through in terms of both a hard glacier bed environment and also perhaps in a soft glacier bed environment. There's lots of theories about soft bed surging as well as rigid bed surging, but you could, to begin with, think of soft beds as behaving in a similar way to the rigid bed, except that the tunnels that are closing down aren't tunnels in the ice above the bedrock, they're tunnels or channels or pipes within the substrate, canals within the substrate that water can drain through efficiently when the canals exist, and water doesn't drain through efficiently when that canalized drainage system is closed down and water has to escape through the sediment itself. Now there's a lot of work on this, and it's developed over many decades through periods where people didn't really have much of a clue about what might be causing surging, and people were saying, oh, it's all to do with earthquakes, or it's all to do with this, that and the other. But in the end, all of those theories were kind of knocked out because they might apply to one particular glacier, but it wasn't a general theory of glacier surging. And then with ideas such as the subglacial hydrology and thermal or hydrological switching theories, people began to get a handle on what was actually going on in surge situations. But there's been a lot of recent work, particularly by Sylvester and Ben et al. I've put the papers on the KLE for you to read, where they've been trying to draw together a general theory that encompasses all of our understanding of what it is that's driving glacier surging. This is pretty difficult stuff for you to maybe get your heads around on a first glance, but I've put the papers on the KLE and you can have a look and try to tie back what they're saying in this new work to the ideas that you've encountered, for example, looking at CAM, or as we've just been talking through some of the basic ideas in the last couple of minutes. Now that really was a very fast run through, barely a mention of fast flow and surging. I didn't want to get bogged down in it or talk about it in too much detail because it isn't a major topic for the course that we're doing at the minute. If you do want to get into it in more detail, then there's links into the literature on the KLE, and there's an opportunity to take it as a topic if you want to for your coursework essay. There may be questions about surging, brief questions at least about surging in the end of module assessment as well, but as I say, it isn't a major topic that we're really dwelling on. So for now, I'm just going to give you these conclusion points. Different glaciers flow at different speeds. We already knew that, but we can break them down into the categories of some glaciers, ice streams, for example, going at very fast flow speeds, some glaciers going at intermittent faster and slower speeds, surge glaciers, and a lot of glaciers flowing at the normal glacial flow regime, flow pace. To some extent, that can be due to subglacial hydrological controls that cause instability in glacier motion. And we've seen again here that motion, hydrology, temperature, all these controls, all these factors that we've been talking about over the last few weeks are all closely connected. Whichever topic we choose to look at, surging for example, we need to be bringing in ideas from different parts of the course. And this goes back to what we talked about earlier in this section about you developing your conceptual map of how everything hangs together. Try to stick surging on there in the same way that I asked you to put fluctuations in there. Make sure that in your map you can see these connections between different topics. And at the moment, one of the things that's useful for is because it gives us a heads up as to what we need to talk about next. And over the next few weeks, as well as beginning to look in a bit more detail at exactly what the characteristics of the ice bed interface are, we obviously need also now, it's clear now that we need to look again at temperature and basal hydrology in a little bit more detail. So that's what we're going to come on to in our next step of this module.